Hello everyone, thanks for watching this video. My name is Zhang Jianzhao. Today I'm going to talk about our work, deep in words rendering for practical object appearance scan with uncalibrated illumination. Digitalization is an important goal of computer graphics computing communities. Digitalizing the real physical world enables lots of applications. It provides abundant shapes, appearance, data for virtual realities, augmented realities, and the movie industry. Object shape, surface material, and lighting conditions jointly decide how the objects look like. Modeling these three factors are the key objectives of digitalization. And in this paper, we focus on material appearance. Humans can easily distinguish virtual objects generated by renderings. High-quality object appearance reconstructions enables realistic renderings. Comparing with low-quality reconstruction, it delivers better visual effects. Object appearance is usually modeled as a SOV-based model. SOV-based is the high-dimension function about distant lighting direction, wave direction, and spatial coordinates. Therefore, to recover accurate object appearance, then sampling lighting directions is needed. As the figure shows, that dome is often adopted for such purpose. Usually, these object captures need special devices, but our goal is to build a lightweight system with only off-the-shelf devices to recover SOV from an arbitrary number of input images. About related work in these sections, one straightforward approach to capture appearance is brute force measurement. Researchers will design professional devices to control lighting and camera view for such purpose. Home devices are light stage. They are mounted with large number of lights and able to provide instant lighting from different directions. Although this method is able to recover vivid appearance, the dedicated devices hinder them from consumer applications. Recently, learning-based methods rely on deep learning technologies to efficiently recover SOV maps. Newly methods focus on planar objects. Representative methods are from Li et al. And Decomposition et al. Li et al. Capture images under neural illumination and take single images and input further unite. Similarly with Li et al., Decomposition et al. Utilize similar neural networks but show images under flash lighting. However, this method takes only one image as input. They often fail when visible reflectance features are insufficient to distinguish ambiguities. The new method tries to increase more input images for SOV predictions. Go et al. Present a novel framework takes an arbitrary number of input images and input, sharing the same idea to utilize multiple images. Then Decomposition et al. Adopted an order-independent fusion layer to combine uncalibrated flash-lit image features. However, this method focuses on near-plane materials. In contrast, our method is able to recover object appearance. About object appearance recoveries, Li et al. Proposed a learning-based method to jointly recover shape, SOV and illumination from only a single images. Like previous single input image method, it may suffer from insufficient observation. Another related work is from Kant et al. They utilize large optimal lighting patterns to capture object appearance. Comparing with Kong et al., we aim to recover object appearance with only off-the-shelf devices other than specially designed equipment. In this section, I will briefly talk about our method. The input for our method is an arbitrary number of flash-lit images, which is captured in a dark room with all indoor lighting switched off. The output of our method is as-a-variety property maps, including diffuse, specular roughness, coefficient maps, and normal map. There are several assumptions here. We assume all input images are captured in a fixed view, and all images are lit by the same flashlight. During captures, the flashlight is always facing the target. Therefore, the flashlight could be modeled as a point light. Besides, for each input image, assume the flashlight position is unknown. Before diving into details of our method, let's have a glance of the framework. We adopt similar deep inverse rendering framework like Gao et al. As the figure shows, a decoder with parameters fixed generates as-a-variety maps from latent code Z. After a differentiable rendered images are sent to calculate similarity loss, then optimize planar material as-a-depth in a blurred latent space. Such deep inverse rendering framework has following advantages. First, it's flexible about the number of input images. XMP make it as-a-variety scales from plausible to accurate. Second, third, especially trained small latent space is suitable for optimization. Third, it is able to embrace point light position as variables, and it allows light position unknown for each image. Therefore, we adopt deep inverse rendering as our basic framework. Then let's talk about how to model object appearance. As the figure shows, a smooth body plus brown planar material samples equals a brown body. The body surface can be viewed as warped planar material samples. Since we decided to model surface material in the lit space, I hope the lit space focuses on material itself. Usually, object appearance in fixed view can be modeled as diffuse, roughness, specular, and normal maps. Normal map is related with surface material and its shape. Since we hope that this space focuses on material characteristics, we needed to decouple shape and surface material first. But global normal in curved view is related with detail, geometry, and basic shape. We utilize a detailed normal map to model geometry detail, and we utilize the base normal map to model large geometry, which is related with its basic shape. Then let's have a look at 2D slice of object surface. Origin means origin object surface. At point B, we have normal vector, and P illustrated in orange. We want to decompose the origin shape as base shape and planar material samples. In base, normal NB, P is related with large-scale geometry variance. In planars, normal vector NDP is only related with material itself. Specifically, given normal NBP, we can judge local coordinates system CP in such local space. Detailed normal NDP means variation from base normal NBP. Accordingly, transformation from detail normal to global normal is a simple matrix multiplication operation. Once normal is decomposed as detail normal and base normal, shape and surface material are decoupled. Object surface material characteristics modeled by diffuse, roughness, specular, and detail normals can be encoded in the space exactly like planar materials. With the help of object mask, we can dilate object as rebranded maps so that there is no void space in those images. Then we can directly adopt the trained model from Gao et al. Without any modifications. In the work of Gao et al., SRBRDF's autoencoders training with random rows and smooth localizations, it is demonstrated that a smooth space is suitable for optimization. Then let's have a look about deep inverse rendering stages. Our framework consists of 3 stages. First is the initialization. Second is the deep inverse rendering stage. Third is the refinement stage. Initializations include reflectance and lighting initialization. We utilize state-of-the-art works by Li et al. As our initialization method. It takes a single co-located lit images to the cascading networks and predict SRBDF's normal and depth maps. Estimated normal from Li et al. Is used to initialize base normal, and the flattened normal is used to initialize detail normal. Then SRBDF maps goes to encoders to get initialized latent code Z. About lighting initializations, so all images are captured with the same bright light. So the intensity of light is invariant during captures. Therefore, only point light positions need to be estimated. To initialize point light positions, we adopt the try and compare strategies. We predefine several light position candidates and render images according to the initialized SRBDFs. Then we compare them with measurements and find the best candidate. Next stage is the deep inverse rendering stage. It's the key stage of our method. As the figure shows, decoders whose parameters are fixed generate SRBDFs from latent code Z, then along with light positions and base normal variables. They are sent to render images, comparing with measurement, constructed loss drive network to optimize the code estimated light position and base normal. The last stage is the image space refinement. In our optimization network, SRBDFs are encoded in the bottleneck of the autoencoder. It usually decodes reflectance property maps with the detail lost. This thus will add post-process step to refine SRBDF property maps pixel by pixel. And this slide is about keyframe selections. Usually more encoded images captures under different illumination help dissolve ambiguities and achieve accurate effects recovery. However, there is always a trade-off between quality and cost. Unfortunately, we do not control light position. Therefore, optimal illumination is not available for us. Then we decide to directly select images where targeted object shows the distinctive appearance. Photographs look similar, they are possibly lit by flashlights close to each other. Here we rely on the classic K-means clustering method to divide all captured images into different clusters and select central as pick images. In these images, we show examples of K-means clusterings. And in this figures, we show selected images for burning. We can see that selected images have different highlight area, and this highlight area uniform covers the whole body of burning. In section, I will show results in these papers. First, we render 401 images for each synthetic objects, and we select 24 images out according to k-means clustering result. As shown in this slides, we can see that after optimizations, associative property maps are very close with reference, and as the byproduct, light positions converge to ground truth dramatically. And this is examples of bunnies. We can see that our method can recover bunny normals with more details, and we can distinguish diffuse and specular effects clearly. And we also compare our method with classical inverse rendering, that is, directly optimize all variables. We can say that our method outperforms classical inverse renderings, and the classical inverse rendering method mainly have some artifacts in both diffuse and specular coefficient map. We extend our method to real acquisition data. Figure illustrate how devices are deployed in a dark room. Camera A mounted on a tripod shoots video of target object, while camera B only serves as light source, and it is moving in front of target. We show reconstruction result for oval. 24 file images are selected from videos. Since there is no ground truth as regarded for real objects, we render images under novel lightings and compare them with real captured images. We also render these images with environment map. This slide is about results for Adobe Rabbit. It shows that our method is able to reproduce strong specular effects. This is the result for wooden ornament. It demonstrates that our method is able to handle diffuse effect. In conclusion, we propose a lightweight method to recover object reflectance with uncalibrated fresh lightings. Modeling object surface material in a pre-learned space enable our method to always recover reasonable SRBI depth and constrained optimization routines to reduce ambiguities. Our deep inverse rendering framework efficiently takes estimated normal SRBI and light position to construct render laws so that our method can be flexible with number of input images. But future work, one limitation of our method is that we cannot interreflections among object components. Our method may fail when an object contains large particle area. Therefore, in future we will handle multiple bounds reflections spatially. Currently, our method may fail if other indoor lightings are not switched off. This is because when the flare light is moving, other uncontrolled lights cast wearing shadows on the target object. Thus, we consider an accurate shadow detection model in the futures. We would like to thank anonymous reviewers for the valuable comments, and we would also to thank material and model provided from Dan Chencho and Guide. This work is partially supported by the NSFC and is also funded in part by the University of Macau. Thank you. This is now time for 10 minutes question.